Okay, guys. So what I'm going to do now, I'm going to talk about, Ito's lemma. And I'm not going to formulate Ito's lemma directly. What I'm going to do, I'm just going to show you a couple of examples of how you can derive those kind of things. Okay. So our basic object that we're going to look on is this WT guy. Okay. So this is just going to be like x for regular functions. Okay. And what is this WT? So when we talked about it in the class, I told you, okay, that you need to actually imagine a time axis from 0 to t1, let's say, okay? And then you take each of these t1s and you divide it into small units, just like when you do integration, okay? You divide these guys into small units, and then you can actually look on those guys, on those intervals, right, on those disjoint intervals as independent entities, okay? And in each entity like that, you're going to generate a random variable which is normally distributed, okay, and which have a variance which is proportional to the length of this guy, okay? So you can think about this heuristically as being basically a time series of daily returns, let's say, of a stock, okay? So these guys, these small guys, will be your daily, daily occurrences. And in each day, you're going to measure, right, your opening price, your closing price, and you're going to calculate the return, okay? Now, the basic premise of financial risk management and all these kind of assumptions is that, the return here and here, and both of those two are independent. So it means that if you have daily return today, you do not know whether the stock will go up or down tomorrow. You don't know that, okay? You do not know that, and even if you knew that, it will be completely independent, okay, of what the stock did today. So whatever the stock did today, right, does not reflect in any shape or form what it is going to do tomorrow. There is no higher probability of it going up or down depending whether or not it went up or down, right, today, okay? So these guys, okay, these small guys, okay, are independently normal variables. If you have here, right, a sequence of basically, T0s, T01, T0 primes, yada, 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 T0 n primes like this, right? Each one will have basically the opening and the closing of this interval, right? Basically, this is T0, this is T0 prime, etc., etc., etc. The covariance matrix of these guys, right, will be basically, T0 prime, T0 2 primes, yada, 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 T0 prime, prime, primes, and everything else is 0, where T0, right, is going to be the length of those intervals. So those intervals, right, every one of them is going to be an independently normal variable from other ones, so that will be its covariance, right? Whereas the diagonal is just basically the length of those intervals. So these guys, right, are going to be called DWTs. So DWTs are those kind of guys which represent daily return of stocks. Now, when you take those guys together, what do you get? You get compounded returns. Okay. So when you look on this, on the sum of these WTs, or because you have so many, you may maybe want to replace it with an integral sign, right? Which basically is the sum of those guys. Okay, you have basically a compound returns, right? And those compound returns are going to represent, a return on a unit interval. So if you have daily return here and you sum them, let's say for 30 days, you're going to get basically a total return in 30 days. Okay? If you have a year annual return, you're going to sum those daily guys, you're going to get an annual return. WT, right, represents a compound return from point 0 to point t. Okay? So it means that you're fixing a point in the past. Let's say you're fixing a point, let's say 3 weeks from now, 3 weeks ago, right? And then you sum those returns until here, 3 weeks is W21. Okay? So this WT has actually the following, the following thing. So WT is actually normally distributed, right? And T is actually the length of the interval. But what is very interesting, that the covariance of WT and WS is not going to be 0. It is going to be actually equals to minimum of TS. Okay? Why is it going to be equal to minimum of TS? Because you can think about WT, right? It's a compound return until time t. So it's going to be equal to the compound return until time s plus the compound return for the time t minus s. Okay? So if you are actually if you are here 21 and this is 10, right? So the compound return until 21 equals to the compound return here plus the compound return here. Okay? So it's WT equals WS plus WT minus S, and then covariance of WT, WS, right, equals to covariance of WS and WT minus S. But because S and T minus S are independent, this covariance plus covariance of WS with WS, right? But because WS and WT T minus S is independent at 0, so you're going to get that this is covariance of WS, WS, right, which is actually equals to S. Okay? Now, if, right, so S is here and T is here, right, so you're going to get S, which is minimum of S and T. Okay? So here it is actually very interesting that those guys do not think that compound returns are independent, right? They are not. They are not. They are not. They are not. In fact, as an exercise, you can actually calculate the correlation of WS, WT, and this is going to be basically square root of minimum TS divided by the maximum of TS. And this is your exercise. Appearance test, laughing out loud. Okay. So this is about WT. Now, so WT, right, is actually going to correspond to the function x. It's actually its compound returns, okay, that correspond to the function s. Now, how do we derive that? Say you have a function f of WT equals to WT squared. How do we derive this guy? Okay, so how do we derive of dWt squared? So if you look on dWt squared, it's going to be what? It is going to be 2WT dt plus the second derivative, which is half times 2 times, dWt squared times dWt squared. Remember that I'm using the formula f of x plus delta x minus f of x, or this is basically df of x, right? This is equals to f prime of x, delta x, plus half f2 primes of x, delta x squared, divided by 2 factorial plus higher order terms. Here, right, dWt squared is actually proportional to dt, okay? If you think about Wt as being compound return, it has an average of 0. However, when you square it, right, Wt squared, the expected value of Wt squared is going to be t, because t is a variance of Wt squared, okay? Now, when you look on changes, this has to come up in some shape or form. And it comes in some shape or form exactly here. Okay? So this is going to be 2WT dt plus, and here half and 2 goes away, and you get dWt squared. Now this is going to be basically the dt. So it's 2WT dt plus dt. dWt, sorry. Okay? So what does this formula tells you? This formula tells you that if you take the Wt squared and you look on its change, you are actually going to get some non-trivial contribution from the non-random component. This non-random component comes from the fact that the expected value of dWt squared is not 0 anymore. Okay? It's actually proportional to the variance. Okay? And the variance here proportional to dt. So that's why it's coming into play here. If you, for example, right, take another function, say you get e to wt, it will be the same logic. So if you derive it once, if you look on ewt, right, what do you get? So you get ewt times dwt, And then the second derivative is 1 over 2, right? 1 over 2 factorial EWT, DWT square, which is going to be basically EWT times DWT plus half times EWT times dt. Okay? So this dt once again creeps in. Okay? This dt is actually once again comes from the fact that dWt square, right, is not 0. The expected value of dWt square is dt. So when you shrink the interval, okay, when you shrink the interval, the randomness, you could think eventually that the randomness goes away. But here, right, what the randomness will not go away totally because you have this dWt square, which is going to be dt. Okay, so you have two examples here, right? It's actually pretty straightforward how to do it. In general, okay, if you have basically a function, which is a one variable function of the fwt, right? When you look on this guy, you're going to get the following. You're going to get basically f prime wt times dwt, but then plus, and now you're going to get half times f prime of wt's, right, times dt. And this dt is because dwt square, right? So this is Ito's lemma. This is basically what is called Ito's lemma in its most elementary form. But what I want you to do, right, is to actually repeat this derivation again and again and again and again. Do not recall, do not remember the formula. Repeat this derivation again and again and again and again, because it's going to be much easier for you to remember when you are going to go into the Black-Scholes world. You will understand exactly what's going on. There you have more variables, but exactly the same principle applies. Okay? So that was the video. It was a short video. I hope that you enjoyed it. It's actually very important one, this guy. And I'm going actually to talk about next time, maybe I'll do a video on that as well, how you can derive the Black-Scholes using this kind of mechanism from the CAPM. Okay? So it's not going to be the usual derivation of Black-Scholes, which is kind of, relies more on hedging arguments, but it's going to be Black-Scholes, which is derived from the CAPM. And I'm just going to derive the PDE. I'm not going to solve it. All right? So have a great day, and I hope to see you soon.